In this video, I'm going to be going through the last parts of bending. So what I'm going to talk about now is I'm going to talk about uniformly distributed loads, and I'm going to talk about, I'm going to solve some of the past HSC questions. I'll quickly go over, with the knowledge that we have of bending moment diagrams, to cover a little bit in detail, revise the three that I've gone through in more detail. And then we'll go through some of the more difficult questions. So the concept that we're looking at here is that if we have a simple beam, and what we want to do is we want to have, let's say we have a 100 kilo weight, or 100 kilo mass, which would be 1,000 newtons. Pretty easy to tell me what the reactions are. What's the reactions on that? 500 on each side. Yeah, you should be able to do that straight away. If it's symmetrical, the loads are going to be symmetrical. And in that situation, well, what is our shear force diagram going to look like? Well, once upon a time there was a beam, and it went up 500, and then it went across some number of meters, and then it went down 1,000, and then went across the same number of meters, then went up 500. Pretty simple. And then what would, let's say that for the sake of the argument, we'll say that L equals 6 meters. So this is 3 meters and 3 meters to each span. So what is our maximum bending moment? Well, we could use a couple of methods. What we could do is we could use the M equals FL on 4, or PL on 4 as it's often written, which would be 1,000 times 6 divided by 4. Picked an example, so that'd be 6,000, 6,000 divided by 4 would be 15, right? That sounds about right? And that's in Newton meters. Okay, that's one option. Another option is we could say, well, the left-hand side, the moments on the left-hand side equal the moments. So if I say the sum of the moments at point, we'll call this point H. The left-hand side plus the right-hand side equals 0. Well, if we look at point H, remember that this point here, this 1,000 newtons, it has a, what's the distance from point H, that 1,000 newtons? 0 meters. So in that case, we can kind of ignore, but if we go, so the left-hand side is going to look like this. It's going to have 1,000 times 0, and it's going to have 500 times 3. We're going to have a turning moment of, it's going to be going clockwise, of 1,500 newtons, Newton meters. Or if we look at the other side, well, we're going to have that same 1,000 newtons. This is the left-hand side. The right-hand side, what we're going to get is 1,000 newtons times 0, which is 0. And we're going to go across, we're going to have 3 meters, so we're going to have 500 times 3, which is again 1,500 Newton meters, but this one's going to be going anti-clockwise. So that when we have 1,500 minus 1,500 equals 0. So we've proven it that way. That's the second way we can do it. The first way is using our rule. Now it's important to remember that our rule here will only work for a simple beam. That means it can't have more than one reaction, right? In everything we do in the HSC is always a simple beam with only two reactions, right? It can't be continuous. It has to be symmetrical, and it has to be with a single load mid-span. There's a lot of caveats there, but for the HSC that's very, very common. Now the next way we can do it, and this is the way I would typically think about it, and this is the approach that I think you should take. This is kind of tedious. This works, but it doesn't work all the time. What I like, the best way is I like to count blocks. So the thing I did last time when we were counting blocks is I said, let's call this block A, or block 1, and this block 2, and I've put dots there to help me remember. So what I do is I say, well, we have to start at 0, and that's because if we say that the left-hand side equals the right-hand side, we just saw here that the left-hand side equals the right-hand side in the middle. If we go all the way to here, the left-hand side equals this minus this. Does that make sense? This area here minus that half of it equals that. Yeah? If you take this area minus that block equals that. But once you get to 0 meters, there's now no longer enough. Eventually getting to the point where if you go to 0 meters, that thing has to be 0 because there's no left-hand side of that. Yeah, so what that means is that when we get right all the way to here, well, this minus that is 0. Yeah? So that's how I approach it. And so we know that it has to start and finish at 0 at the end of the beams. It doesn't have to be 0 at the reactions, it has to be 0 at the end of the beam, because we've learned that already that there can be cantilever beams. We talked about how Copeland says he loves a good cantilever. Okay, so what we've got here, what is the area of block 1? We started at 0, what was the area of block 1? 3 times 15 equals 1,500, so I'm going to write that 3 times 15, or I like to write it as force times distance. So 500 brackets 3 equals 1,500. Okay, and then what we're going to do is we're going to add this block. So what we're going to do here is we're going to add this block, which is 1,500 plus, now what are we adding? We're adding minus, this is 500 below the line, negative 500 times 3. And so what we get there is we get 1,500 minus 1,500 equals 0. And we're back to 0. So that makes sense, yeah? Now, where it's a bit more confusing is when we divide this force, and we're going to say that it's going to be, I wish I had picked 6 meters. We're going to say it's 100, you know, we're just going to do it. We're just going to say, we're going to get different force. We're going to say that it's going to be 100 meters. We're going to say it's going to be 100 each meter. So 1 meter, 2 meters, yeah. 1, 2, 3, 4, 5, 6. Yep. Anyway, all right. Okay. In this space, in this situation, well, what's our reaction going to be? What's our total load? 600, so we're going to have 300 on each side. Yeah. Okay, so if we were to look at our shear force diagram, we're going to start off by going up 100, and then we're going to go half a meter across to the center of our load, and we're going to go down 100. So we're now here. And we're going to go across another meter. Well, actually, if we did it exactly like it looks here, we'd go start at 300, and then we'd go across, down to, and then it'd go across, and then down, and then it'd go across, and then it would go the same thing again. So 1, 2, 3, it'd go across 1, 2, 3, and that would be our load, yeah? Does that make sense? Now, if I was to calculate all of those blocks, I would get a thing that, well, let's do it. Okay, so let's look at it. I'm not super excited about this because it's tedious, but we're going to call that block 1, and we know that it's going to be symmetrical. There we go. So that we'll do it this way. Okay, so the first block is half a meter tall and times 300. So it's going to be half times 300 is 150. Oh, it's going to be a straight line to 150. Okay. Let me type it in. All right, let me write it in here. 300 times half equals 150. Okay, and the next block, it's 1 block wide, but now it's only 200 tall. So what we're going to do is we're going to add on 1 block times 200. So 1 block times 200 is going to be 200. So what I do is I take 150 plus, I'll write it in, 200 times 1 equals 350, yeah? I'm writing the answer above just because I want to. Now at the end here, I've got another block. It's 1 meter, but it's only 100. So if I was 350, and I'm going to add 100 to that, what am I going to be at now? So is it 350 plus 100 times 1 is going to equal 450. 450 Newton meters. Now, what we can see here is that we had a graph that kind of goes like that. It's curved. It looks sort of curvy, right? Now, if I said that this was uniformly distributed, it wasn't just in chunks, if I just had an infinite number of arrows, well, what I'd get then is I wouldn't see steps. I would see a straight line. And what I would see here is I wouldn't see steps here either. I would see a curve, a parabola. And that's what we get when we use uniformly distributed loads. So to compare, and we're going to look at this in a second, to figure this out, the actual value here's what's really important. In the HSC, they can ask you to recognize the shear force diagram. This is a free body diagram. They can ask you to recognize the shear force and bending moment diagrams for uniformly distributed loads, but they can't ask you to calculate them. Now, for me, to show there is a formula, and it's commonly used, which is m equals little WL squared on 8. So that if you knew that it was 1,000 newtons per meter, so you'd write 100 newtons per meter times 6 squared is 36 divided by 8. And let's see how close that number is. 100 times 36 is 36 divided by 8, 450. The same answer we got. Yep. Okay. The fact is, we're not going to worry about that because it's not something we get in the course. Now the thing is, writing all of these arrows, you can't write that enough arrows, right? It's a bit painful. So what they do instead is, it's like they just take this part of the arrow, they just take the arrow head, and they actually even remove that, and what they do is, typically you just draw it as a bunch of curves like that. That's how you draw a uniformly distributed line. Sometimes you will see it as a bunch of arrows, but this is much more common, especially for hand calcs. When you're drawing calculations by hand, that's how you'll draw it. And you'll say, little w equals 100 newtons per meter. That's how I would write that. Okay, so we've now understood what a uniformly distributed load is. I just want to write this down here so we know that we're talking about UDLs is uniformly distributed loads. Right? I think there's also, you can buy cans of UDL, but I wouldn't know too much about that. Okay. Let's see what Copeland has to say next. We're listening to the Avatar bending song for 10 hours. If you can hear that. It's just that for 10 hours, pretty soothing, nice and relaxing, not too taxing. Okay, so for uniformly distributed loads, we do need to be able to recognize that what we predicted here, that when we see, if this was a single point load, we would see this. We'd see rectangles on the top and triangles on the bottom. When it's a uniformly distributed load, what we see is triangles on top and curves on the bottom. Now let's have a look here. So where we have a point load, we see rectangles and triangles. And when we see UDLs, we see triangles and curves. And if you can match up the triangles and curves, you're going to have a good time. Okay, so what we're going to do now is we're going to look at, as a guess, we're going to look at 4, and we can see how they go. So you know what? Actually, let me use this as that. Okay.
squared.
Okay, we have here 4 free body diagrams. Free body diagram A, B, C, and D. What I'm going to do, rather than make you guess them, I'm going to go through and we're going to draw what we think our shear force diagrams should look for each of these. So we'll start off with A. You know what, actually, we can guess. We'll start by guessing. And then we'll go from there. Makes these things a bit more worthwhile. Okay, for A, which free body diagram do you think matches for A? We'll do it this way. For A, which free body diagram matches for A? A is the free body diagram. Which shear force diagram matches for A? Let's have a look. We've got a uniformly distributed load past a cantilever. We've got a reaction going up, and then we're going to have some sort of diagonal. We're going to have a line going up and then diagonals down, and then we're going to have a sudden drop. So let's have a look. Here, if we start, remember we always start and end at 0. In all of these cases, we start and end at 0. So here we start at 0. We're going down, 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 like a Coles ad. And then we're going to go up straight, a big amount. And then we're going to go down, 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 up, big down, 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 up. Can you see which one matches? Yeah, okay, so I'm going to draw what I just said there. It starts off at 0, and it's going to go down, 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 big up, down, 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 big down, 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 up. Which one matches that? Okay, are we going to do the whole thing, or are we going to, yeah, let's do, and then we want to go, so we'll do shear force diagram, then bending moment diagram? Yeah, okay. So we've found the shear force diagram. Which is the bending moment diagram that matches that? So we're going to click on bending moment diagrams. Okay, so I've got an answer here already, the fourth one. We'll see how we go. So to start off with, we have a triangle, so that means we're going to have a curve. We've got this area here, it's curvy, right? So it's got a triangle on top, so it's going to be curvy, right? And then we're going to have triangle there as well. So what we're going to have is a line that goes something like that. Yeah, which we can see as the fourth one. Okay, because there's no square areas there. So good, we're done. Let's go to the second one. We can start the second one here. I'll get rid of this. So which one do you think? It'd be great if I could shrink that a little bit.
You can move the browse a bit up out of the window.
How do I move? Oh. Look, that'll close to doing, isn't it?
You can move the other one out of the window. You can put that, and then click on the other one. Yeah.
Okay, good job. Okay, so now we can see all of them. Okay, so I'm just going to write here uniformly distributed loads, or UDL. Okay, so for number 2, well, let's have a look. So our shear force diagram, we're going to go up, or I'll write here, we're going to go up, we're going to go across, we're going to go down some amount, we're going to go across, we're going to go up, and then we're going to go down. Now I don't know the exact values, so I don't know if I'm going to match it. So you can see that mine doesn't quite look like that because I didn't know how much down we had, but there we go. Okay, so which bending moment diagram is going to match? Well, first of all, this area is positive. So we know this area is positive, then it's going to be a triangle. This area is going to be a negative triangle, so it's going to be something like that. And then this is going to be a positive curve. Now I know it has to end in 0, so it'll probably be something like that. Probably going to be something like that. Let's see if we can find, oh, there we go, it's here. Okay, great. Let's see if we'll do C. What do we got for C? I've said we're going to be starting at 0. We're going to go up. We're then going to go across, not doing anything. We're then going to go down, 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 and we're going to go up. So that one, let's see, is... Oh, the first one. Yeah, excellent. Okay, thank you. Okay, so what is that going to look like? Well, this area here is going to be a triangle, and then it's going to be some sort of curve. It's going to be curving positively, right? And then it's going to be curving negatively. So I don't know if it's going to be curving in or out. I should, but I'm a little off my game here. Which one do we have here? Oh yeah, it is like that. Okay, how do you know if it's going to be curving in or out? What you think about is you think about how is this beam going to bend, right? I think my beam's going to bend like that. Whereas here my beam is going to bend like that. And this will give you an idea of, if you think about how your beam is going to bend, so we've already done this one as well, so it's going to bend steeply and then down like that. That will give you an idea, but I'll show you here, that it'll give you an idea of what your bending moment diagram is going to look like. This one will look like this. And when you think about what it's going to bend, you then flip it upside down, and so what we're going to get is we're going to get a diagram that looks something like this. Whoops. I just don't know the exact values. Okay, so they're going to inflect it the other way. Okay, so let's have a look. What we're going to get for our shear force diagram is we're going to start at 0. We're going to go down, 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 up. We're going to go down, 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 and then big up, down, 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 down. Okay, so we're going to start off in an area below the line. It's going to be negative, and it's going to be curvy because that's a triangle. It's going to go above the line, and we're going to add because it's going to be curvy because that's a triangle, and it looks symmetrical. So, well, it doesn't look symmetrical, but what we'll say is we've then got an area below the line which is curvy. It's symmetrical up here, so that should be symmetrical here. And finally, it's going to be an area that's above the line, so it's going to be getting us back to 0. And we always start and finish at 0, and it has to be curvy because it's a UDL. Okay, we're good? We think we've got those? If you can recognize that, I think you're going to do pretty well. So, let's start looking at some past HSC questions and be done with bending. Okay. Just very quickly, we'll have a look at this. This just confirms what we know. I'm going to reiterate. From point load, we're going to have this going to be equal to half on each side. It's going to give us a block shear force diagram. And for point loads, we get rectangles and triangles. For UDLs, for uniformly distributed loads, we get triangles and curves. And we can have combinations. Here we can see that if it's a UDL there, it has to be a diagonal, and if it's a diagonal, it has to be a curve. And that's probably the easiest way to approach these. Okay, let's get some more questions going. Okay, a shear force diagram is shown for a loaded as shown. Now, we haven't done this sort of question before. So what we're going to do is we're going to say, well, where is the position of the maximum bending moment going to be? Now, with shear force diagrams, we know that maximum bending moments occur at what location?
They cross the axis.
Where they cross the axis. So that means that given that we only cross the axis at one point, it's going to be B. Now, another way we could look at it is we could remember that the shear force diagram, what will it look like? Well, we're going to have an area in block A that's going to go up. We're going to then have another area in block B. Is that bigger or small? It's probably a little bit bigger, so it's going to go up. Then we're going to have an area that's going to go down a little bit, and then down a little bit, and then finish. That would be what I think it would look like, and we can see that it in fact lines up. So without any numbers, right, this is a good question because it means that it's just showing your understanding without really numbers. Okay, I think we've looked at this question before, but let's have a look at it. No, maybe not. The drawing represents a loaded steel beam simply supported on each end. Which diagram best represents the distribution of shear forces along this beam? Okay, well, let's tell the story. It's going to go up. We'll use this line as our shear force diagram. Up, it's going to go diagonally, then it's going to go steep down, and it's going to go maybe like this, because it's symmetrical. And then it's going to go down a little bit more, and then up. I didn't use any values, but that looks pretty good. That looks like A. We okay with that? Excellent. If we had to draw the shear force diagram, it would look like, sorry, the bending moment diagram, it would look like it'd be above the line and be curvy, and then a little bit, so it probably looks something like that. Do you want to move up here, and then that way you can click for me?
Are you doing all of these?
Okay. So, what is the position of the maximum bending moment? I think we've looked at this question before. 2014 was looked at before. We've said that maximum bending moments occur where we cross the axis. So it's either going to be at A or C. Now, to figure out the bending moment diagram, if we're going to draw the bending moment diagram here, this line will be our 0 line. What are we going to have? Well, this is going to be 2 times 4 is going to be 8. And then we're going to go down because this is minus 1, so we're going to go to 6, 8, 6. Here we're at minus 4 times 4, so we're going to go to minus 10. And then we're going to go 5 times 10. Now, the question here is, this is an interesting question. If this was a concrete beam, and we needed to put steel in this concrete beam, what we would do is we'd have some amount of concrete that would probably run through the entire bottom. It really could stop there, so let's say I said stop there. We're then going to add extra steel, maybe around here, because this is where there's a lot of bending on the bottom here. So that's one way of showing extra steel. I've said before that you could draw the line, you could draw it as steel and another row of steel, or if the row, the extra steel is in line, it would be shown like that. You don't need to know this. This is late uni concrete design, but I just want to give you the idea. What's really important though is you need to have steel in the top for this whole area. So I might have steel and steel there, because remember, steel needs to go where we're in tension, and this side is, here we have tension on the bottom and tension on the top. Remember, it's the opposite of the diagram. The bending is going to look like that, so we're going to have tension here and tension here. Yeah? I'm using this opportunity to say, why do we do bending moment diagrams?
So you can see where the extra steel.
We can see where we need to add extra steel. We can also see where we might choose a different material. We might choose a higher grade of concrete, not really with concrete, but theoretically. It's also, we could reposition our loads. Yeah, we might redesign based on, we might say this is not good enough, we can't deal with this, we're going to have to redesign. So there's some other considerations we might look at. Okay, in this situation, if we would, let's say it's a steel beam, I wish the church said if it was a steel beam, we would just take the absolute value. Now we've said before that absolute values mean we don't care if it's a minus or a plus. I think the answer should be C, right? Because that is the biggest, that is the most extreme value, and that's what we'd be designing for steel. For a solid steel beam. For concrete, we need to know both values. And that's why we can't just say, what is the maximum bending moment? We need to know, well, we need to know the story so that we know how to load our beam, where to position reinforcement. Okay. Can you click on the next one? Yep. Okay, we've looked at this one, I think, before as well. So we're going to draw, so it says, which one represents the bending moment diagram? Now, I'm okay with this, where I did this with a student this week, and I said, okay, well, what's the bending moment, the left-hand side of this load here? What we've got is 9.4, and we've got 8. Now, remember we said 8 brackets 0 is 0, so we can ignore that. We've got 9.4 times 3.5, which I'm pretty sure is 32.9. Yeah? So if we can identify, well, that's the bending moment at that location. We didn't need to draw any shear force diagram. But maybe it's easier to look at it if we do draw it as shear force diagram and we can figure out the load cases. What we can say is, well, okay, our bending moment diagram, we're going to go up 9, we're going to go across 3.5 meters, we're going to go down here, and then we're going to go across 3 meters, and then we're going to go down 12, and then we're going to be, so 10.6 below. Okay, which one looks like that? Well, if we look here, we're going to take our diagram. Now, it's worth pointing out that diagrams can be written upside down. Yeah, many designers want their diagrams to reflect the bending on the beam, and the beam is definitely going to bend in that shape. So many designers show they invert their diagram. So I would not take the direction of the diagram as a given. I would look at the values. So what we want to see is our maximum should be where we cross the line, which is here. So our maximum is here, but our maximums are also here and here. So I think we can eliminate B just because the maximum is in the wrong spot. Yeah. Okay, we can also have a look and see, okay, the next thing we can see is, well, what we've got in here is a number that's positive, and then a little bit more positive, and then a big negative. Yeah? So that really, I mean, we've already said that it's A, but we're really honing in on that it has to be A, given this particular load condition. Yeah? This kind of really needs to be a cantilever to explain how we could get this load condition here, and here we have just the wrong values. When we actually do a calculation, we see that we get the wrong values, and aside from the fact that the diagram is inverted. Okay, the diagram being inverted shouldn't be enough to rule it out, but the answer is A. Okay, click on the next one. Okay, cantilevers. Now we've talked about cantilevers before, so this here is a fixed cantilever. If I need to find out the maximum bending moment, we could just do this question now. They've told us that there's a 15 kilonewton force and 5 meters. So that means at point H, what have we got here? Well, we've got we're going to have 15 going up just to balance that equation. Yeah, some of the forces vertically, 15 down, we need to have 15 up. But the problem is we're going to have this turning moment. We're going to have this thing that wants to turn the whole plane around. So what are we going to do to balance that? Well, we need to have a moment at the fixed location. So how we often show that is this, and we draw a moment, and we're going to say a moment couple at the plane, right, at the joint. So what is the value of m? Well, in order for that to be equal, we're going to have to say that the sum of the moments equals 0 at point H. I've just chosen H because we were using it earlier. And so I've said 0 equals 15 times 5, which I think is 75. Which is that going clockwise or anti-clockwise? We said clockwise is positive, so it's positive, minus MC. So it means we can move MC over to here, that's algebra, and that gives us 75 kilonewton meters. Yeah, because we used kilonewtons and meters. We don't like kilonewton meters, so we're going to instead change that to 75 times 10 to the 6 Newton millimeters. Okay, what's our formula for bending stress? Determine the maximum value of bending stress. Yeah? What? So sigma B equals mi over I. Okay, so we've calculated m. What is I? The y bar. The y bar, can you define y bar?
Is it the thing where you take the average of
The y bar is the distance from the neutral axis. This is the neutral axis. And it's the distance from the extreme fibre to the neutral axis, which they've told us y equals 200. Actually, no, they've said 200 total, so that means that y is 200 divided by 2 equals 100 millimeters. Yeah? Okay, they've given us a value of I, which is 26, so let's write that in here. We've got 75 times 10 to the 6 times 100 millimeters divided by 267 times 10 to the 10 to the 6. Okay, well, great. We get to cancel out those 10 to the 6s, and so what we're going to get is 7,500 divided by 267 equals, cancel shut, thank you, equals 28 megapascals, right? Because we used millimeters, and we used newtons, and we're going to get our answer in megapascals, because we go together like megapascals and millimeters squared. Okay, so that gives us our answer of the bending stress. I'm not going to check it, but sounds cool. Okay, we're clicking, yep. Shear force, we've already done that one. Clicking, we've already done that one. Okay. This one, I think the answer in the book may be wrong, which I'm hesitant to put a video out there and make a big claim. But what we can say is, in this situation, we've got a symmetrical beam. So what's our loading going to be? What's our reactions going to be? 5 and 5. If our total load is 10 and it's symmetrical, we're going to have 5 and 10 divided by 2, which is going to be 5 and 5. So we're going to go up 5, we're going to go across, down 5, going to go across, down 5, going to go across, going to up 5. Yep. Okay, good. What's our bending moment diagram going to look like? It's going to look like that. Our maximum bending moment is going to equal this value of this block, which is 5 times 5, which is going to be, well, I'll write it here, 5 equals 25 times 10 to the 6 Newton millimeters. The rest of the values, okay, so what value of y are we going to use? So that's our neutral, they've told us that, I'm going to draw that beam bigger so you can see it, it's 70, so the value for B is 70, the value for D is 300. We know that D is not twice as important, the value of D squares, so the bigger the D, the bigger the value of I. Yeah? So it's very important, the bigger the D, the big D gives us a stronger beam. So in that case, our neutral axis is going to occur halfway because it's a rectangle, yeah? Which means that that's our neutral axis. Our Y value is going to be the same either way. And so our Y is going to equal D12, which is going to equal 150. Okay, they'll show you, yeah, we're going to see a question like that in a second. And then they have the I value there. If you can then apply that, I'm not going to do the calculation because I'm not sure the answer is right. I've given you the pieces of how I would solve the question. Next one. Okay, so this diagram shows a 6 meter beam. So L equals 6, F equals 8. So we can say M equals FL on 4, which is 6 times 8 on 4, which is equal to 12. And that's 12 kilonewton meters, which is the same.